So we go over derivation of continuity equation, and for which we consider control volume. There are two procedures through which we can see, as we have discussed in the kinematics of fluid flow, the Eulerian way of seeing things and the Lagrangian way of seeing things. In one case, the observer is fixed and the body moves, and in the other case, the observer moves with the body. So this is a similar situations also. We consider a control volume. We choose the volume arbitrarily, and either we keep it fixed and let the body flow past it, and then we try to see how the equation behaves. Or in the second case, we can see that we can keep the fluid moving through the or with the object. As we see in the picture, the fluid is moving from left to the right direction. The control volume is indicated by the dotted line. The fluid does not move through the body, and it does touch the boundaries though, and so in the interior volume it's supposed to be a closed box. But in another form, the fluid is moving through the box, so they are different frame of reference, different conditions, different way of observing things, and we will apply different approach for developing the equation. To derive a differential conservation equation, we imagine a shrinking volume to a small infinitesimal size. We choose a very small box, very small control volume, and that is why we call it infinitesimal, because as you know, when in calculus, when we see a small change in x, we denote it by either delta x or in this form dx. And then we try to say the limits. Let's say if we are observing it with respect to time, then we see the change in x in a small time, and these things are denoted by delta x by delta t. And when we want to calculate its value, we take the limit such as delta t tends to 0, meaning it shrinks. Delta t tends to 0, that is, it goes to the minimal possible value, and that is what they are trying to say this in the same way. So we choose a small control volume, but for the sake of convenience, that box, that control volume is enlarged, is shown here in a very enlarged picture, and rectangular coordinates are here for our calculations and computations of equations. And as usual, the x, y, z direction are taken in the three-dimensional case. They are shown on the box as well, and the dotted line shows the direction of the rectangular coordinates. When we have seen the fluid moving in and out, then we see that the conservation of laws of conservation of mass says that the fluid cannot be created nor maintained. So from the left hand side, when we see in the first picture that I showed you that there is no fluid that is moving in, and so on the right hand side, all that I have to see is how the fluid is that is moving out, and that will be delta rho by delta t into dV. That will give me the rate of change of density, the mass, times the volume. The total mass will be obtained, and then at the same time I have to see how much is the velocity, the total mass again is given. So one, I have control volume. Over the control volume, I see how much fluid is moving, and this is giving me the mass. Rho into volume is the total mass of the fluid that is moving. And this is equal to the mass that is coming in and minus the mass that is going out. So the net rate of change of mass within the control volume is equal to the rate at which the mass is flowing into the control volume minus the rate at which the mass flows out of the control volume. And it is shown by this equation. The dot means a rate of change of m with respect to t. The quickest and most straightforward way to derive it in the differential form is done with the help of Gauss's divergence theorem. What we know from the knowledge of vector calculus, that the Gauss's theorem helps us to convert a volume integral and it relates with the surface integral. And therefore, it is a famous theorem which tells us that a divergence of a function g is the function here of the variables, times dv, that reflects the volume. So this integral is over the volume so that it covers the total volume that is there in the control volume that we talk of. And this reflects with respect to the surface volume, and this is the volume. This will tell us that is coming out of the surface that is in consideration. So with the help of this integral, this theorem, Gauss's theorem, we derive the continuity equation. And for this value, therefore, we can write down the value in the form. So using the Gauss's divergence theorem, which is this, in this equation on the right hand side here, we see that can be written as divergence of rho v into the dv, and this v is not velocity, it is the volume. The two integrals can be combined together because now both of them for control volume, and that was the advantage of the Gauss's theorem, that it related the volume integral with the surface integral. So we combine the two, and the integral over the control volume becomes delta rho by delta t plus divergence of rho v into dv is equal to 0. This 0 has been brought to the right hand side. Now this equation, this is only possible or valid if the integrand is itself 0, and therefore delta rho by delta t plus divergence of rho v is equal to 0, where rho is the density and v is the velocity vector. Del is our vector operator. So this equation in vector form is known as continuity equation, and we have derived it using the Gauss's theorem. Equations of an immense value. Basically, it says that the mass is conserved, which is the law of conservation of mass.